So let's take a look at Newton's equation. So what Newton actually said when he was talking about gravity was that we have a force of gravity. So this is the force of gravity. Force of gravity. And he said it was equal to m1 times m2 divided by the radius or distance between the objects squared. So m1 is the mass of the first object, m2 is the mass of a second object, and r is the distance between the objects. And he said basically that, so I have, for example, the Earth, and I have the moon. Okay, so this distance of r, and then this object has a mass, and then this object has a mass. The force of gravity between them would be equal to this equation. Now later we had a scientist by the name of Miles Cavendish who came along and said there's actually this factor called G, and it's all because what Newton said was close, but it wasn't exactly correct. And so until Cavendish came up with the G, we've added that in, and now we have the gravitational constant, G, times m1 times m2 divided by r squared, and we get mass. We get the force of gravity. This may be familiar to some of you because you may have learned the electric force is K Q1 Q2 over r squared. So they're very similar equations, and it's this similarity, this pattern that we've noticed, that leads us as scientists to come up with ideas like string theory and looking for theories of unification, where we're trying to connect all these forces that occur in nature and describe them with one equation. We haven't done that. Even though they look similar, we haven't been able to do that quite yet. But our research at the Large Hadron Collider and the research we're doing surrounding the Higgs particle and all that kind of stuff is working towards trying to unify these two ideas, the electric force and the gravitational force, trying to put them together. Okay, so just like we did with this one, we're going to take a look at the math with this one. So let me move over here. So the gravitational constant, G, equals 6.67 times 10 to the negative 11th power. The units is newtons times meters squared divided by kilograms squared. Okay, so what does this times 10 to the negative 11th look like? So what this means is, well, let's take an example. If I do 1 divided by x squared in your math class, you should know that that's equal to x to the negative 2 power. So x to the negative 2 means I'm dividing by x squared. So what does this mean? This means that I'm dividing by 10 to the 11th power. So this is going to be a really big number with lots of zeros. And if I divide by that, I'm going to get a really, really tiny decimal. Okay, so what I thought I would do, because this is a conceptual physics class, when we are not going to actually do this calculation, I thought I would show you the calculation just so you would appreciate what's going on. So G times m1 times m2 divided by r squared. And what this is right here is I've taken a 1 kilogram bowling ball, and I've placed it on the surface of the Earth. So object 1 is the Earth, object 2 is going to be the bowling ball, and then we have the distance between them. So here's G, there's my bowling ball of 1 kilogram, here's the mass of the Earth, here's the radius of the Earth. I plug all those numbers in my calculator, and I get the force of gravity equals 9.8 newtons. So I did a bunch of math with a bunch of numbers to get 9.8 newtons. Force equals mass times acceleration. That's what we just finished looking at. So if I plug these same masses into this equation, I get 1 kilogram times 9.8 meters per second squared. I get 9.8 newtons. So the equation we've learned for the force of gravity on the Earth, okay, mass times the acceleration due to gravity, is equal to the same force using Newton's equation. Okay. So what I want to show you though is if this was not the Earth and this was the moon, we would get a much different number because the actual acceleration on the moon is 1.6 meters per second squared. And so we would get 1.6 newtons. Does that change the size of the bowling ball or the mass of the bowling ball? No. It just means that the moon's mass is less, so it's going to pull on it less. Okay, so mass doesn't change, but the acceleration can change because the mass of the other object can change. Okay, so let's take a look at some generic situations from a general standpoint, and I think this will make more sense. So we've run this with some numbers, but we're going to actually take a look at it in terms of how we did with our electric force equation, where we're going to talk about it just in general, okay? So if we're going to pretend that our mass, we have a mass of 1 and a mass, so m1 is 1, m2 is 1. The distance between them squared, or the distance between them is 1. If I plug them into my calculator, we're also going to pretend that g is 1. 1 times 1 divided by 1 squared. What does that all mean? The force is 1, right? Because 1 times 1 times 1 equals 1. And 1 squared is 1, and that equals 1. Okay? What does this mean? If I were to look at this, this would mean that I have the same situation that I set up just a minute ago. It would mean I'm going to multiply whatever force I have times 1 because I haven't changed the masses. Okay? So let's change it, and this will make more sense what I'm trying to say. Mass 1 is 1, but I'm going to double the second mass. So instead of a 1 kilogram bowling ball, it's going to be a 2 kilogram bowling ball. So a 2 kilogram bowling ball would be 19.6 newtons because I'm doubling my force. Well, let's check it out here. If I pretend that G changed, no, G didn't change. M1 changed, no. M2 doubled. R squared, R didn't change. So 1 times 1 times 2 is 2, divided by 1 squared is still 2. So if I doubled my force. So if I double the mass, I'm going to double the force. Okay? So if this was 2 kilograms, I doubled the mass, so now the force is going to double. I could even do it up here. 2 kilograms, I plugged all of this in my calculator, I'm going to get 19.6 newtons. I doubled the force. Okay? So what about this one? I tripled one mass and I doubled the other mass. So 3, actually G didn't change, so it's 1, times M1, which is 3, times M2, which is 2, divided by 1 squared. 1 times 3 times 2 is 6, divided by 1 squared is still 6. I'm going to multiply the force times 6. What if I do this? Now I'm going to keep the masses the same, but I'm going to bring them farther apart. Okay? So what does that look like? G is 1 times 1 times 1 divided by 2, but don't forget to square it. So that's 1 divided, what's 2 squared? 4. So the force is going to drop by a fourth. So if I cut this by a fourth, if I doubled this to 12.756200. Okay, and then squared it, did all the math. My ultimate force at the end of it would be 1/4 of my starting force, which would be, what is that? 1/4, 2.45? 2.45 newtons, 1/4 of 9.8. Okay? So I'm not going to make you do all of that math, but you should be able to recognize this by doing this process. Okay? Now we got to watch out when we do this, just like we did the last time. 1 times 1 times 1, because these are not changing. G never changes. Divided by 1/2, and now I'm going to square it. So I'm going to get 1 over 1/4. And when we divide by a fraction, we got to multiply times the reciprocal. And so this is going to quadruple the force. So if two objects with mass are closer together, they're closer together, I cut the distance in half, then it's going to quadruple the force. So this one, so up here, all of these are saying we started with an object here and an object here, and they stayed that way all the way down because the distance is staying the same. This one, I double the distance. Okay, I double the distance, so the force drops by 1/4. Go to this one, I cut the distance in half, and the force multiplies times 4. So we're going to do this substitution method again, okay? So I'm going to give you some practice problems so you can practice this, as well as answer some questions about the nature of gravity and weight and mass. There will also be some 7-step problems you'll also have to work, which will be very similar to what you've already been doing because it's force, okay? All right, thank you.